Hey everyone. So today we're going to talk about modulations. Unfortunately, Stack doesn't have like a good concise chapter of this where you can follow through and get to what we need to do for the lab. So this lecture is going to be kind of a blending of an amplitude modulation note that I posted on Canvas. And there's also additional notes on phase and frequency modulation that I'll have you read through so that you have the information for this particular set of lectures on modulation and demodulation. There's also a really cool video on Canvas from Sabine Engineering, same person who made that transistor video, made a really good video on modulation and demodulation also. So let's talk about what a modem is. You probably heard of modems when you have to deal with your internet service provider. But if you were growing up in the 90s like I did, or watch some old videos like the net or something like that, you probably might have heard sounds like this. Let's just see, I'm gonna play this. Let's see, cover. I just did it. I think the mouse might work better. There it goes. So that's the modem dialing an actual phone number. Okay. And right now what the modem is doing is actually negotiating both the frequency and the phase and the amplitude of the tone. I'm going to try and talk about what this is. If you can hear me, maybe not. Okay, so that's what a modem sounds like. And in fact, if you go on Wikipedia, this is probably like the first modem ever or something like that. It's literally a telephone handset that you put onto the modem, because the way modem works back then is basically what the computer information, the data that's sending out of the computer, like just ones and zeros. What the modem actually does is that it converts it to electrical waves, because telephone actually send information via electrical signal, right? And these are modulated waves, and it's sent through the telephone network and received on the other side from your internet service provider, and then your internet service provider demodulates it on the other end in order to get to the data and then send you whatever you requested back. Okay, through the same process but in the opposite direction. Okay, so that's how modem used to work. Even when I was growing up, it didn't look like this. It's just a card you put into your computer, and it has a little telephone jack that you can plug into, so that it actually connects to the telephone network, and then so that's therefore your your parents cannot use the phone at the same time as you're using the internet, and they get really annoyed by you. Nowadays, modems kind of look like these. It's just kind of boxes. Some of them may even say modem on top of it, but like maybe like this is something you get from your internet service provider, or maybe something flat like this, and there's some blinking signal on it, and there's some cables in the back you have to connect in order to get the data and the power supply. Okay, so a modem that works through the telephone network is known as a digital subscriber line. I don't think these are around anymore. I don't know if still people have those. These are pretty one of the older ones, where it's basically like an enhanced version of your telephone line, and it's able to do the modulation, demodulation for you there also. But the same technology works on cable. So I think in my house it's still a cable, because the cable infrastructure is just so large that we can't get away from it. So that's the same cable that basically gives you your cable television, that's also providing internet. So some of you guys might have fiber optics cable running into your house, and these will be a completely separate cable just for data, for internet data. But if you're using a cell phone, or in my case using a Wi-Fi signal here, Wi-Fi and cell phone uses wireless transmission, but that also requires modulation and demodulation, and even more because it's being sent through the airwaves. We're going to see why that's the case. If you're communicating with satellite, you also need modulation and demodulation, and we're going to see why. Okay, so if you're sending some signal, and usually that's going to be a low frequency thing. For example, my voice ranges from about 100 hertz up to 20 kilohertz. Well, maybe not my voice. My voice is probably about 400 to 500 hertz most of the time. But let's see. But these tend to be, the information we're sending tends to be lower frequency. And for example, here, this is actually a 1 hertz wave, so not that low frequency, but it just makes it easy to draw, right? So let's call this our signal, Fs, okay? And we're gonna modulate it with a carrier frequency, Fc, right? That's much higher in frequency. So this is the 20 hertz wave. Typically, you would use like gigahertz or megahertz instead. But the reason I'm using 20 is so that we can actually have a plot. Because if I draw a megahertz wave, it will just be a solid green box here. Okay. The way you modulate things is by multiplying the signal and your carrier together. Just take the product of it. Okay. And I'll show you how in electronics we can actually do this. Okay. And what happened is that the modulated wave turned into this blue one, so that has a lot of wiggle in it. Okay, so I call this the wiggle, technical term. But there's also a lobe to it, right? Let's not use red because red is the actual original signal. Let's do black, right? These lobes, okay? Those of you who remember your wave analysis in your general physics class, these are called the beat frequencies. These are where the signal gets, the amplitude gets large and then small, large and small. And it's not due to the wiggle, it's due to the fact that you have this modulated signal inside your product wave. Just to be a little clear, typically in general physics, they would teach you how to add. This is due to adding and subtracting wave. This is due to multiplying waves together, okay? And we're going to see how that kind of turns out to be the same thing. Okay, so the black, the lobes, right? Let's call it lobes, not loops, right? Those are kind of, the lobes are kind of the similar frequency to what your signal is. The wiggles is from your carrier, okay? So why do we do modulation? Well, one of the first reasons, let's zoom in here a little bit, is just not practical to have to be able to send and receive signal that are very low frequency. Okay, so for example, as I mentioned, right, human hearing is about 200 to 20 kilohertz, right? So if you were to transmit this as a sound wave, right, like me just speaking to a person, okay, the speed of sound is very slow, 300 meters per second. So if I was sending out a 1 kilohertz sound wave, okay, the wavelength of that will be 30 centimeters. The way you figure this out is that, well, the speed of sound is the wavelength times the frequency. If you want to figure out the wavelength, right, you just take the speed of sound divided by the frequency. Okay. Okay. And in order for something to be able to hear the sound wave that you're emitting, right, the device that you're used to listen to it has to be somewhere on the order of that wavelength. Typically, can be, maybe a factor of 10 smaller, but you don't want it to be too small, because what's going to happen is that wave basically just passes through that object as opposed to interacting with it. And that's why humans evolve this thing called a cochlea. Is actually inside my ear, well, two my ears. And it's evolved to be this long duct, long as in, several centimeters long, right? In order for us to actually hear lower frequency sound. Because if you just want to hear very high frequency sound, you just need a little hair at this tip here. That's why at the beginning of the cochlea, you hear high frequency sound. It's actually much deeper the longer part of the cochlea, that you actually detect the higher frequency sound. Sorry, lower frequency sound, longer wavelengths. Okay, that seems to be reasonable, right? Okay, something on the order of a few centimeters. My phone is about that size. My mouse is about that size, right? My computer is actually bigger than that. But what if we were sending this information through electromagnetic wave instead of sound waves? Okay, so right now I'm speaking into a microphone here. That's a sound wave. But then once that microphone, right, detects that sound is actually going to be transmitted as an electrical signal. An electrical signal is almost at the speed of light. There's a little bit less because you actually have the electromagnetic waves actually go through wires instead of a vacuum. But right, the speed of light, right, is about 3 times 10 to the 8, right? So the wavelength of the electrical version of my voice, instead of being 30 centimeters, is 300,000 meters, right? Much, much bigger, right? Just because the speed of that medium, right? Because I literally just pipe in the speed of light as opposed to the speed of sound, right? And in order for us to receive the signal, right, you need an antenna. And the way that antenna works is basically when the electromagnetic wave passes through it. So in this case, the waves is, right, going towards this, right? There's a positive part of the electric field. The positive parts of the electric field actually draws electron towards it, right? Okay. And then the negative part of electric field pushes the electrons away from it. So this actually will be positive on this end, actually. Okay. And it's this difference on the two sides of the electric field, right, that tells you, that basically drives a little bit of current. And then if you pass that current through a resistor, then you would get a little voltage out, right? Okay. And you want this antenna somewhere on the order of the wavelength of that wave, because, right, if it's much smaller, right, you will not catch the entire amplitude of the electric field that's passing through it. So the smaller your antenna, the smaller the amplitude you're going to be able to catch on your electromagnetic waves. Okay. So in order to catch something like this, maybe you want something that's at least a factor of 10, about a factor of 10 smaller, right? So 30,000 meters, right? That's a big antenna. That's from from Turlock to Modesto, right? That's 30 kilometers. Okay, so hopefully you guys don't see 30 kilometer size antennas everywhere, right? So that's why in the practical sense, you don't want to send these 1 kilohertz signals around, because you just don't have antennas that can receive it. Okay, so if we change the frequency of the signal to be 1 gigahertz instead, and modulation will allow us to do that, right? Now the wavelength is going to be 30 centimeters, right? So that means, if you have a device that's the size of your phone, the size of your mouse, right, the size of your computer, you will be able to receive the signal still. Okay. The other consideration is that since we live on Earth and all devices live on Earth, most of the devices live on Earth, there's also a atmospheric noise. This atmospheric noise is plotted here, and I found this on Wikipedia also, where basically the amount of noise in the atmosphere, as you increase in frequency, it goes down. So if you were dealing with, let's say, a 1 megahertz signal, right, your noise level will be about 30 decibel, because it's on decibel scale here, right? So the horizontal is frequency, the vertical is basically the noise in attenuation, noise in in dB, right? Okay, that's the same scale that we use when we were dealing with gain versus the same decibel as the attenuation that we got, right? So, and remember that attenuation in decibel, right, is actually a log scale. So anything that's twice, if I double the decibel, right, it's not a multiple of 2 in gain, it's actually a multiple of 10 in gain, okay? Okay. So in this case, right, so if I, start at 1 megahertz, so 30 decibel is noisy, but maybe we can deal with it. But if we go down to 100 kilohertz, right, 0.1 megahertz, right, the noise that you're going to see from the atmosphere, which is what this blue band is telling you, was measured in the UK in the morning when there's very little noise around, I guess, right, you go up to 90 decibel. Okay, so that's a factor of, well, if you go to double, you get 60, you could double it again, you get to 90, so that's a factor of 20 bigger in noise. Okay, and then if you go down to 10 kilohertz down here, right, it's even go up, it's not even on the scale. Not to mention 1 kilohertz, you will never be able to hear any actual information. You would just be drowned in noise. Okay, so that's why when we're sending signal, we tend to have maybe a megahertz or above in order to do this send. Okay, so where does this noise come from? So electrical noise from the atmosphere is basically due to atmospheric convection, where when you have molecules moving around, sometimes these interaction will move charge from one place to another, just like if you're rubbing, what was it, silk with glass, right? You develop static charges. Some of these charges moving around will create electromagnetic field, and when you're also in the ionosphere, the ionosphere is the upper part of our atmosphere where the sun actually has enough energy to basically ionize the molecules in the ionosphere, hence the name, right? Those charges moving around also causes noise in the atmosphere. And whenever there's lightning, so some of you guys might know this, when you're talking on the phone or watching TV or something, when a lightning strikes, it actually does a little flick. It actually flickers the signal that you're getting. Okay. Let's see. So if we try to transmit anything, around kilohertz, you're just going to hear noise. You're not going to see anything that's your actual data. Okay. And this is where modulation comes in. So I'm going to go through in detail how we do amplitude modulation. Okay. And this is what we're actually going to do in the lab. I'm still trying to decide whether or not we're going to go through phase and frequency modulation. They're very similar to amplitude modulation, but it's just a different thing where we're varying in order to do that. Okay. But amplitude is the easiest to understand, so let's start with that. Okay. And the way you do amplitude modulation, or actually any modulation, is with triangles. Okay. So when you know about triangles, you have these things called trig identity. Specifically, we're going to use this one here, where it's basically going to be cosine, the product of two cosines, and then it turns it into actually sum of two cosines instead. Okay. We could use the sine and combination of the two, but just to keep the math simple, let's just deal with the cosine version of it, because your signal could be sines and cosine combined together, right? Okay, so the plot up here, let's go up here, go up, right? This FM here is written here, right? It's the product of cosine 2 pi t, which is a 1 hertz, and then cosine 2 pi 20 t, right, which is a 20 hertz carrier. So let's just make this, the signal, and make this the carrier. Okay. Typically, as I said, right, the carrier is actually megahertz, where the signals may be something on the order of a few kilohertz. Okay. Okay. So what you see here is that the modulated function, right, which is a wave that's propagating out, right, has some amplitude due to the signal. So we'll keep that there. And has some frequency of the signal. So instead of writing 2 pi's all the time, I'm just going to use omega instead, times the frequency of the carrier. Okay. I'm not going to write the amplitude of the carrier. Typically, the amplitude of the carrier actually is much bigger than the signal, but it doesn't matter, because that you can scale that however you want. And you're going to see that actually changing the amplitude of your carrier doesn't mean change what you send in, what you receive. So it doesn't matter as long as it's strong enough so that it gets to the end point where you're sending it. So we're just going to make that 1 for now, just to make the math a little cleaner. Okay. Remember, one of the key things that we're going to use is that, well, we're going to make sure that the carrier frequency is much bigger than the signal frequency. Okay. Okay. So how does modulating a signal, right, help you with making smaller antenna or having it deal with the noise less, right? Because you're still sending a low frequency signal with a high frequency carrier, and it's actually the low frequency signal you actually care about, right? Not the high frequency carrier. And this is where triangles solves the problem. If you use the trig identity above, right, the product of two cosine function is actually the sum of two cosine function, where the first one is the difference between the two frequencies, in this case the carrier minus the signal. Okay, the second part of that sum is the cosine of the sum of the two frequency, in this case the carrier frequency plus the sum signal frequency. Okay, and then there's a 1/2 in front just because for the trig identities. Okay, so the reason this makes it nice is because now, right, omega c, let's say that's 1 million, right, and let's say your signal is 1 kilohertz, so your carrier is 1 megahertz. Let's just deal with f when I'm talking, right? But when I'm writing, I just use omega, right? Let's say your carrier frequency is 1 megahertz, right? Your signal frequency is 1 kilohertz, right? 1 million minus 1,000 is still about a million, right? It's 999,000, right? Okay. Similarly, if you add 1,000 to a million, you still get about a million, right? So these two are actually sum of two high frequency waves. Okay. Right. So therefore, the modulated frequency, right, which is actually in reality, right, the carrier frequency plus or minus the signal frequency, right, is approximately basically the same as the carrier. Okay. So therefore, right, whatever antenna you're designing, right, all you care about is actually the carrier frequency. You don't care about the signal frequency at all. Okay. So if I was building a Wi-Fi router, I only need to care about how well can I transmit and receive 2.4 gigahertz. I don't need to know, is it going to be a male person speaking who has a lower frequency versus a female person speaking, right? So it's really nice. It actually also makes it so that the transmission is kind of oblivious to what the data actually needs to be. All you have to care about is the carrier frequency. Okay. One more note before we move on. I think I always talk a little bit about this, but this is going to be much better illustrated now, right? So this is the red here, right, is your signal. You can write, right? Red is the signal, right? The blue here is the modulated, right? So notice that one period, let's say if I start here, right, go down, go up, I end up at the same point going down as opposed to going up. This is one period, right? T of the signal. Okay. Notice that the blue has two lobes, right? Okay. There's two lobes per TS, per the period of the signal. Okay. And this is because, right, you basically have a combination of two waves. One is omega c one is omega c minus omega s, the other one's omega c plus omega s, right? The difference between these two frequency gives you this beat frequency. Okay, so the beat frequency is basically 2 times whatever your signal is. Okay, which is sort of neat. Okay, so now that you modulated your signal, your wave, right, and then you send it out into the air or through your fiber optic, through your DSL modem and stuff like that, right? How does the receiver demodulate it? Okay, and naively, where you think, well, if you multiply by something to undo that, you divide, right? Well, dividing is difficult because these are trig functions and analog, and you have some point where one thing or the other is 0, so you don't want to divide by 0 either. Okay, So the way you do this is you basically do the multiplication again instead. Okay. So here, right, the demodulated signal, the demodulated wave is the signal times the original modulation. So this is actually FM here, right? Oops. Right. This first two part of the product is FM. Right. This is what you actually receive. Okay. And then you just multiply it by another factor of cosine omega CT. Okay. Once again, the carrier can have a different amplitude, but I'm just going to leave that as 1, just so I don't have to carry a bunch of ACs around. Okay. So once again, you use your triangles. In this case, right, the two things that you're multiplying together is omega cosine omega c times cosine omega c, which is actually cosine square omega c, right? But you just use this identity here, right? The two arguments here are the same, right? So the x is omega ct, the y is also omega ct, right? Therefore, right, this actually first term here is 0, and cosine of 0 always gives you 1. Okay, hence this term. Okay, the other one is the sum of them. So this is omega t plus omega c times t, right? So you get twice. Okay. So of course there's a 1/2 factor from the identity. Okay. So and then you distribute this fs into it. So the output that you demodulate by multiplying by another factor of omega cosine of omega ct once again, right? You basically have your original signal with half the amplitude plus your signal function times cosine of twice the omega c, okay, which is not right, which is a high frequency. So this part here is going to be your low frequency signal, right? And this is the high frequency part, high frequency, right? I can't write Q, right? So if you have something that has low frequency and high frequency, what do? Right? You put it through a low pass filter, right? All you have to do so to demodulate the signal, first thing you do is you multiply it by by the carrier frequency again, okay? And then you put that through a low pass filter, then you're done. And then you get your original signal back, right? I mean, you're gonna have to amplify because you lost half the amplitude in this transition. Okay, so that's kind of neat. In theory, on paper, right? Some notes on this. Okay, so in order to do this thing, this is called full modulation. Okay, the carrier frequency and the phase has to be the same between the modulator and demodulator. Okay, if they are slightly different from each other, you're gonna degrade the signal substantially, even just like a 1 hertz difference between the two. Okay. So chapter 17 in STEC, the chapter that covers phase lock loop. I'm not sure I will be able to get to it for this class. Talks about how this actually works, and this is done by this thing called a lock-in amplifier. And this is actually what your internet modem is doing when you plug it in. The first time you maybe not first time, when it bugs out and you lose internet, it's like, oh, the first thing you do is you plug it in, plug it, right? When you do that, right, and you may see like a little yellow blinking light that says syncing. It's like, what is it syncing, right? Well, what is syncing is actually syncing the frequency between your modem and the internet service provider, so it has exactly the same frequency and also the same phase. Okay. So the carrier frequency has to be locked into each other in order for your modem to be able to transmit data thoroughly. And this is actually a little board that's going to be maybe not this big in your modem. And this is basically the signal that's coming in, and this is actually the synchronization signal that comes in sometimes from your internet service provider. Okay. And the way this this little chip is doing. This is the multiplier chip. This does the multiplication. I'll teach you how actually it does that on the next lecture. And what it does is that it detects the signals coming in, and it's basically just changing the frequency slightly and the phase slightly in order for it to detect, oh, this is where the biggest signal is going to be. And it's going to send that data back to your internet service provider. Well, is this actually what I'm supposed to see? And then this internet service provider will tell you yes or no. And then if it says no, then it does it again. And therefore, the two systems sync both this frequency and the phase together using these things called lock-in amplifier. Okay, so that's the how full modulation work. And then I will see you on the next lecture.